Okay, now we go to fundamental problem 8.2, right? So you have a cantilever beam, okay, fixed at this point, at one end, left hand, and then at the right end, you have 100 kilonewton load applied to it, right? And then the question asks you, what happened to the state of stress at point A, okay, which is, this section is cut at 0.5 meter distance from right hand side, from the right end, right? So you cut 1.5 from there, and then you see this section, right? Top, bottom, right? This point A is with this dimension, right? This is 300 millimeter, this is 100 millimeter, and then it is, this point A is 100 millimeter from the bottom, right? First thing first, when you cut, you need to find what is the state of internal loadings, right? You cut, you take left or right, doesn't matter, it's up to you, but probably the best way is to take the right hand side, isn't it? Okay, so you cut, you take the right hand side, right? Here you have 400 kilonewton. This is AA, okay? And then this is 0.5 meter distance, alright? So what else you have here? Of course you have V, right? You have V going up, which is 400 kilonewton, okay? You should be able to do this from chapter 6, right? And then another one is you have this, since you have this moment, 400 kilonewton times 0.5, right? So you have that one, the one which counter it, which is 400 kilonewton times 0.5, right? Which is 200 kilonewton meter. Is it okay? Okay, this is the moment countering the 400 kilonewton times 0.5. So you have two interloadings here, like in chapter 6, when you draw the beam, the interloading for beam V and M, right? Okay, so due to these two internal loadings, what happened with this? We look at this point A, right? For this 400 kilonewton going up, just imagine actually it goes up this way, right? So the axis is perpendicular to it, right? Same goes to M. M goes from top tension, right? Bottom compression, isn't it? From this way, moment. So again, the axis is the same for in these two. This V and M, they share the same neutral axis. So how about this rectangular cross section? 100 by 300, isn't it? So it is a rectangle. So actually it is simple. The centroid or the neutral axis, for in this case, it is simply half of that. Okay, neutral axis, right? Half of this. The result is simple. You can find that actually, but here is don't have to, right? The answer is because actually it's too simple to find out, right? You can use formula, but that's fine. Even you can even actually this neutral axis for y and for x and for y here actually it is 50 and 50, right? Half of that, because this is a rectangle. As simple as that, right? The reason why we need to determine this NA neutral axis is because later on when we want to find because for this V you will use this tau equals to VQ over IT, isn't it? While for this M, you will use sigma equals to MC over I, not MC, minus MY over I. Alright? And this point A, it is located somewhere, isn't it? In this case, it is actually in fact 50 millimeter below the neutral axis. 50 millimeter below neutral axis. Do you understand why it is 50 millimeter? Right? Half neutral axis from the bottom, half from the top, right? Because in the middle, this is 100, so this is 50. As simple as that. Below. Okay, alright. So now we'll do this. Okay, first, let's look at this. Of course, looking from this equation, right? You will see that actually you need this. For sigma, you need, of course, y. And also you need I. about neutral axis, and this for tau, you need I and you need Q. Right? So let's do this bending stress first. So you need to find the I about neutral axis. In this case, I about neutral axis is simply what? Half BH cubic, and base is the one which is parallel with intersection 100. Right? So it is 1/12 base. I think I prefer to work in millimeter. Alright? So I think let me change this to 2000 kilonewton. Okay, no. Because it's 0.5, so this is 500 millimeter. Alright? So we multiply them 20,0000 kilonewton millimeter. Alright, you can use SI if you want, no problem. 20,000. Not 0,000. Okay, sorry, not 20,000, 200,000. Alright, 200,000 millimeter. Okay, so 1/12 B base is 100 for the I about neutral axis, right? H is 300 cubic. Alright, and then everything is fine because the centroid of this is the neutral axis itself, right? So your I about neutral axis is, if you calculate that, it will give you 225 times 10⁻⁶ millimeter power 4. Right? Okay, now we find stress due to bending. Alright? So due to bending, sigma of point A equals to minus m y of point A over I. Alright? So m is, okay, this is the thing. While using this equation, you need to understand what you are doing. Alright? This is actually, if you follow the positive sign convention of m and positive sign convention of y. Okay? Actually, the most important thing is that you understand whether it's tension or compression. That's all. If you use the correct sign conventions, like I said, of m and y, and then everything should be fine if you use minus. Here, what happened is actually, for this point, is it minus or plus? This bending stress. The answer is minus. Compression. Because, why? Because, as you can see here, top going tension, bottom going compression. So, neutral axis is 0 for bending stress, of course. Top going tension, bottom going compression. So, for A, it is at the bottom, it undergoes compression. Alright? So, in this case, this is, otherwise you need to use m positive going up, okay, with this minus value. Alright? So it is minus, and the m is 200,000 kilonewton millimeter, and then YA is distance from neutral axis to A, not from the bottom, alright? From the axis to A, which is 50 millimeter, and then the I is 225 times 10⁻⁶ millimeter power 4. And then you hit the calculator. Alright, and then you will get minus 44.4 megapascal. Right? If you hit the calculator, you will get 0.0444, which is in gigapascal. So I convert it to megapascal. Right? Okay, this is due to bending. Okay, sigma equals to my over I. How about tau? Tau of point A equals to VQ of A over I. T of A, of course, but T will be the same. Alright? So for this Q, okay, for this V, it goes up, right? Goes up. It doesn't matter actually, but it goes up. And then the V will be this 100 kilonewton. Okay, I will be the same as here. The T will be 100. It's okay. T of this. Okay, so you draw a line parallel to neutral axis, alright, passing through point A. You will get this T, the same T, right, 100 millimeter. And your Q for point A, what do you have to do? You have to find the remaining area. right? The remaining area is this, right? The centroid is here, right? So what happened with the centroid? How much is this? This is simple actually, simple geometry. 150, 50, 100, isn't it? Okay, 100, half of that, 50 and 50, isn't it? 50 plus 50 is 100. It's okay. This is your y prime. Right? And then the area, of course, it will be 100 times 100. It's okay. So, your V is 400 kilonewton going up. Your Q is y bar prime A prime. So, it is 100 y bar prime times A prime, which is base times height of that blue area, is 100 times 100. It's okay. Divided by I, it is 225 10 power 6 millimeter power 4, and then the T, the thickness of A is 100. Alright, so if you hit the calculator, you will get your tau A equals to 17.8 megapascal, and please remember it goes up, right? Follows this 400 kilonewton direction, right? So if you draw the state of stress of this point A, right? So if you draw the state of stress of point A, I hope you can see from, okay, yes. Okay, this is the surface, it's okay. This is the surface, right? Because this point A is the one which is facing you. Okay, this is the space. Then you draw the rest of the 3D. Doesn't matter it goes this way or that way, left or right, doesn't matter. Alright? But the most important thing is that you need to understand the surface that you, the primary surface is this surface. Okay, this A. Alright, so what you have here, you have for this surface, first you have the compression. Okay? Compression of 44.4 megapascal. Compression to this surface, right? Which is 44.4 megapascal. Okay, of course, you have this compression on the surface, you have the one at the back as well. Right? Acting at the back surface, the rear surface. Another one is you have what? You have this shear stress, 17.8 megapascal. Where is the direction? Direction is going up. See, 400 kilonewton going up. Okay, so 4.8 goes up. So you have this have this goes up, alright. Of course, the complementary stresses. Of course, this one is let me put it value, which is 17.8 megapascal shear stress. Okay, on the surface, and then the rest just have to draw the rest complementary. This one, okay, at the back one, this way. At the bottom goes this way, right? And then this is the state of your stress, right, acting on this surface.